Why is the area under a velocity graph the perfect way to represent the displacement of a particle? Stay tuned for this video and you're going to find out everything you ever wanted to know. Now we're going to watch that animation again, but I've slowed it down. So what's going to happen is that little green X there is going to be the particle that moves. Time is about to start ticking now. All right, I've slowed it down. So we're going from 0 second to 1 second, and bang. You can see that the area above is 1, and the particle moved, it displaced itself by 1 meter. Now watch what happens in the next section when this thing continues to go. Now the particle is going to move through the second. It's going to move from 1 second to 2 seconds. Look at the velocity graph above as the thing moves. Bang, there it is. Now we see that it has moved in 1 second. It moved 3 meters as opposed to only having moved 1 in the previous second. Now here we've done it again for the final second, from 2 seconds to 3 seconds. Look at how much more area is accumulating under the velocity graph. Boom. And now what we see is in that third second, from second number 2 to second number 3, the particle moved a distance of 5 as opposed to 3 in the second second and 1 in the first second. And if you really think about it, that makes a lot of sense, because in this instance, the particle is speeding up. If you look at the velocity graph, it's increasing. And when you think about a particle that's speeding up, it basically every single second, every 1 second, it accumulates more distance than it did in the previous second. And that's why that graph, if you think about how the area works under that graph, it's such a perfect parallel, because as you go on in the first interval, you accumulate a little bit of area. In the second time interval, from 1 second to 2 seconds, you accumulate more area than you did the previous second. And the same thing happens in the third second. Okay, so hopefully that introduction kind of made sense. What I want to do now is take some time to look at, when you're analyzing a kinematics problem from physics. I think, one of the really nice things about it is you can just look at a velocity graph. And we're not going to be using any calculus, but that'll be for another video. But for now, all of our velocity graphs are going to be linear. They're either going to be constant velocity, or they're going to be increasing velocity or decreasing velocity in a linear way. And it's really interesting what you can do with that graph and the problems you can solve without having to memorize a single equation. Okay, so hopefully that video, that animation that you saw earlier for the last minute or two was pretty good and made sense to you. But now I'm going to spend time at the iPad, sort of like hashing it out, trying to explain it. I don't want to say we're going to prove it. That would require a little bit of calculus, but we're going to give a pretty good argument that the velocity graph is king. Okay, look at what we have here. I've got a velocity graph. Okay, now we're going to take some care into exactly what we say. All right, so look, on my velocity graph, if you'll notice, the slope is equal to 0 for that blue line. That means the blue line, the velocity, is not increasing and it's not decreasing. It's just staying constant, and in this case, it's constant at 3 units up. Now, what I want to point out, look at the time. Imagine the time runs from 0 to 1 second. If that happens, that means, all right, well, we can think about it logically in our heads. 3 meters each second, 3 meters per second for 1 second would be 3 meters that we would have moved in a second if that's how fast. Now I want you to look at the picture. Under that 1 second, an area, right? If you stop it at 1, the velocity is constant at 3. And if I find the area of that rectangle, it's 1 times 3. And there's 3 squares there, so the area is 3 for the first second. What that means on the position graph is that my position went from 0 to 3. Assuming I started at 0, I don't have to, but in this case I did. Now let another second pass. So now we go from 1 second to 2 seconds, and if you notice, it sweeps out an area of 3 again. I have a rectangle right there that's 1 by 3. So in other words, I've gone another 3 meters in another second. And there's that. And then I do it for a third second, from 2 seconds to 3 seconds. When the time changes from 2 seconds to 3 seconds, I get another area of 3 on my velocity graph, which equates to another displacement of 3. So I go 3 more units, dotted line there, in 1 more second. And basically, it's not too hard to see that what ends up happening is, number one, okay, the velocity is not increasing or decreasing, so the slope is 0, and the acceleration, I'll just write accel there, that's equal to 0. So that's a pretty strong hint that the slope of the velocity graph is going to be equal to the acceleration. But also, the arguably more important thing here is the area underneath it for each time interval that we go stands for the displacement on the position graph. Now before I scroll down to the next graph, I want to point something out. Over here, the rate at which your position changed was your velocity. Now in this case, my position was changing, if I follow the line through, up 3 over 1, up 3 over 1, up 3 over 1. So the rate of change here, in other words, the slope on my position graph, was equal to my velocity. And since the slope here wasn't changing, then the velocity wasn't changing. Okay? Now, the area underneath this graph actually represents my various displacements. So there's some sort of backwards relationship that goes back and forth. The area underneath the velocity graph tells me about my displacement on the position graph, and then the slope of my position graph tells me what my velocity graph was. And in this example, the slope of the velocity graph was 0. And I said that that was the acceleration. So let's scroll up. Now, pause the video for a second and ask yourself this question. What's acceleration? All right, now hopefully you thought about that for a second. Acceleration, what that actually is the rate at which your velocity changes. So it's almost by definition, here my velocity is changing. And let's count out how it's changing. It's going up 2 for every 1 second, up another 2 for every 1 second, up another 2 for every 1 second. So it would seem to me that my acceleration here is equal to 2. Now let's talk about the units. So I'm going to scroll up a little bit for that. Well, in the upward direction, the units are meters per second. And in the horizontal direction, the units are seconds. And slope is the rise over the run. So if I do meters per second over seconds, if I'm just looking at what the units would be without numbers, okay, I guess I could leave it like that and say meters per second, which is okay, but I'm going to reduce it a little bit. And if you remember that old rule from when you were a little kid, if you're doing this divided by this, it's the same thing as this, meters per second, times the reciprocal of the denominator, 1 over seconds, which leaves us with meters per second squared. So that's the unit associated with acceleration. Now, here's where I think is the more fascinating part. And this is the same example I used for the animation in the beginning. So let's look at this. This is pretty cool. I'm looking forward to this. So from 0 seconds to 1 second, the area underneath the velocity graph makes a triangle, because now the velocity is not staying the same the whole time. Now that triangle has a base of 1 and a height of 2. And the area of a triangle is base times height divided by 2. So in that case, it's 1 times 2 divided by 2, which would just be 1. So what that means is during the first second, the particle moved from 0 up to 1. So I'm going to connect the points in a minute. Right now I'm just plotting them. All right, now let's get rid of this. Oops, didn't mean to get rid of all that. Let's get rid of that and ask ourselves, okay, what happens now over 2 seconds? So in 2 seconds, 2 seconds is right here. I'm going to go up to my velocity graph and I get another triangle and it's bigger. But look, if you compare the amount of area in the first second and the amount of area in the second second, the amount of area in the second second is larger, which makes sense because our velocity is increasing. It's positive, so this particle is speeding up. It started out at 0 meters per second, then it was going 2 meters per second, and 4 meters per second, and it may be 6 meters per second. So since it's speeding up, it would make sense that in the second there's going to be more distance covered. So let's figure out what the total area is. I'm going to switch colors again to blue. Let's figure out that triangle right there. That has a base of 2, and it's got a height, you can count it, of 4. And so then 1/2 the base times the height is equal to 4. So that means all of this area from 0 to 2 seconds is 4. So that means at 2 seconds over here, my position wouldn't be 1. It wouldn't have increased by 1. It actually goes up to 4. So it's there. Now let's go one more second. So let me delete some of this mess in here. All right, we'll go. Okay, now let's do 3 seconds. So when we go 3 seconds, here we go, 1 second, 2 seconds, 3 seconds. That's 3 seconds right there. That's 3. If we count this up, 1, 2, 3, 4, 5, 6. Okay, that makes sense. Our velocity is increasing by 2 every second. So at 3 seconds, this vertical line would represent my velocity, which is 6, and it would be meters per second. Now, the area of this triangle would be, getting a little sloppy over here. Let me just erase a couple things. Get rid of that. Okay. The area of that triangle is 1/2 times the base times the height, which is 18 divided by 2, which is 9. So that means all of this area from time 0 to time 3 is 9. So that means at 3 seconds over here, I'm 1, 2, 3, 4, 5, 6, 7, 8, 9 meters away. I'm there. And now you can see, even if I connected them with straight lines, right, you can see this is not, the position graph's not going to be linear. Okay, now let's just back off there for a second and connect it with kind of a smoother curve. Kind of looks like that, right? Okay, so this would be our position graph, which is based off of that velocity graph. Okay, now let's look at the unit. So let's ask ourselves this question. Why is it, and again, this isn't airtight, but it's a pretty good argument. If you take velocity, okay, I'm going to just draw another picture down here. If I take a velocity graph, okay, so here's velocity, this is time. And remember, this unit is meters per second, and this unit is seconds. Okay, and here's my graph. Area is just the number of little squares you can fit in a given space. That's what area is. So underneath this curve during this time interval, let's take one of those squares. Let's bring it over here and look at it. I'll draw it bigger. Okay, let's look at this. This square, the vertical unit, lines up with the velocity, so that would have a unit of meters per second. The horizontal unit has a unit of seconds. And when you find area, and I didn't put numbers on here, but even if there were numbers, I'd have to still keep the units with them. If I do meters per second, the height times base times seconds, the seconds cancel out, and I'm left with meters. So that's a pretty strong